A droplet in microfluidics is often described as a perfect miniature test tube, self-contained, stable, and isolated. Researchers treat these tiny capsules of fluid as if they were immortal laboratories, carrying reactions, cells, or molecules safely through channels. But look closer, and the illusion dissolves. Each droplet is in constant flux, evaporating at its edges, leaking molecules across its interface, trading surfactants with its neighbors, even merging or splitting under subtle perturbations. The paradox is that what we call a stable droplet is really a system kept alive by continuous instability. Isn't it strange that lifelike persistence emerges only because of constant change? The physics explains the tension. Surface tension fights to keep a droplet spherical and intact, but gradients of temperature, composition, or surfactant concentration constantly tug at it. Evaporation slowly shrinks it. Adsorption and desorption of surfactants alter its skin. Random collisions in crowded channels can nudge it into coalescence. In theory, a droplet should be a fragile thing, gone in moments, and yet in practice, millions of them can circulate for hours in microfluidic devices. Their stability is really statistical, an ongoing balance of fluxes rather than true permanence. This fragility gives droplets their unique character. Because they are never fully sealed, they can act as communicators, exchanging molecules, responding to environmental gradients, even triggering synchronized oscillations. Their very instability makes them dynamic, responsive microreactors rather than static vessels. Like biological cells, droplets persist not by resisting change, but by embracing and channeling. Could it be that what looks like weakness is actually the source of resilience? The droplet life-death paradox also touches something deeper: the parallel with biology itself. Cells, like droplets, are bounded by fragile interfaces, constantly leaking, repairing, and exchanging with their environment. Their apparent stability is sustained flux. Droplets in microfluidics thus mirror the logic of living systems, survival through continuous renewal. Perhaps this is why they are such compelling models for the origin of life. Tiny, unstable spheres that nonetheless maintain identity long enough for complex chemistry to unfold. The haunting insight is that in microfluidics, as in life, stability is never the absence of change, it is change harnessed into persistence. Droplets are born, evolve, and die, yet within their fleeting existence they host worlds of reactions and possibilities. To call them immortal is to miss the point. Their vitality lies precisely in their dance with death. In microfluidics, droplets are celebrated as isolated, stable compartments for reactions and analysis. They act like tiny test tubes that can be generated, manipulated, and tracked with high precision, where stability is assumed to make them reliable platforms for chemistry and biology. However, at the microscale, every droplet is a dynamic object in constant exchange with its environment. Surfactant molecules diffuse in and out, interfaces fluctuate, and water molecules evaporate across barriers. The idea of permanence is an engineered illusion built atop instability. Droplets used for single-cell sequencing, for example, slowly lose volume over time, even when surrounded by oil. It is like thinking a snow globe is frozen in time, while the snow inside is always drifting. Even inside sealed microfluidic devices, droplets are not perfectly closed systems. Water molecules escape through thin films, oils, or even PDMS walls, creating evaporation-driven shrinkage that limits a droplet's lifetime. The process accelerates as surface-to-volume ratios increase at the microscale, making stability dependent on carefully balancing evaporation against replenishment. In this sense, droplets live by constantly dying at their edges. A 20 droplet in PDMS, for example, shrinks significantly within an hour due to water permeation. It is like a candle burning down. Its light persists only because it is consuming itself. Droplets also frequently merge when their surfactant coverage fails or interfaces touch under flow. Coalescence releases surface energy but destroys individuality, making two droplets one. This process is often unpredictable, driven by fluctuations and instabilities, yet microfluidic designs sometimes exploit coalescence to trigger controlled reactions. The act of dying as an independent droplet becomes a way to produce new chemical life. Two reagent droplets coalescing in a T-junction to initiate an enzymatic cascade is one example. It is like two soap bubbles fusing into a single, larger one, erasing their separate identities. Stability hinges on surfactants, which lower interfacial tension and prevent coalescence. But surfactants themselves are not static. They constantly exchange with bulk phases, interfaces, and neighboring droplets. This exchange makes stability a dynamic equilibrium rather than a permanent state, where gradients or chemical reactions can tip the balance and trigger instability. What appears like a protective skin is actually a restless molecular traffic, a wall that exists only by perpetual turnover. Fluorinated surfactants, for example, migrate between droplets in emulsions, altering their lifetimes. It is like a castle wall that stands only because its stones are continuously being replaced. Scientists have learned to harness instability to control droplet life cycles. Controlled evaporation can concentrate reagents, while programmed coalescence can initiate reactions on demand. Instability is not failure, but a resource for timing and triggering events, so the balance between creation and destruction becomes a design variable. Engineers thus build reliable systems from fundamentally unreliable elements, with stability existing only as guided instability. Evaporation, for instance, is deliberately used to crystallize proteins inside shrinking droplets. It is like cooking soup by slowly letting the water boil away until flavors concentrate. At a deeper level, droplets are inherently non-equilibrium systems, exchanging matter and energy with their surroundings. They sustain ordered internal reactions only by dissipating energy and undergoing constant flux, resembling living cells more than static test tubes. Their death is inseparable from their functional life, so attempts to freeze them into permanence miss their true dynamic essence. Droplets hosting enzymatic reactions, for example, both catalyze chemistry and evaporate away simultaneously. It is like a musician playing music that fades even as it is created. This instability may even echo how protocells behaved on the early Earth. Primitive compartments likely formed, merged, divided, and decayed rapidly, yet still supported rudimentary chemistry. Such instability could have been essential for evolution, providing variation and turnover where persistence did not require permanence, only cycles of renewal. Fatty acid vesicles in origin of life experiments, for example, grow and divide by transient instabilities. It is like sandcastles, eroding with each wave, yet inspiring new ones to be built again. For modern applications, droplet instability is both a challenge and an opportunity. Uncontrolled evaporation or merging can ruin experiments and data, but controlled instability provides tools for mixing, triggering, and concentrating reactions. Recognizing droplets as dynamic rather than static helps design robust platforms where devices work with instability instead of against it, turning droplet life cycles into engineering resources. Droplet digital PCR, for instance, relies on stable enough droplets, but also exploits controlled fusion to start reactions. It is like sailing with shifting winds. You fail if you resist, but succeed if you harness them. The paradox is that droplets are treated as immortal reactors, yet their very existence depends on continual processes of loss and change. They are both reliable and fragile, both stable and unstable, with death by evaporation, merging, or exchange serving as the source of life as functional microreactors. Trying to erase instability erases the very mechanism that makes them useful, showing that droplets teach us order comes from dynamic flux, not static preservation. A library of identical droplets in a microarray, for example, shows slight variations in size and content over time. It is like identical twins who slowly grow apart, proving that sameness itself is never absolute.